Welcome to the next lecture on uh, um, rectangular waveguide. In previous lecture, we derived the wave equation, which I will write it here again. Here is the wave equation of magnetic field component in the z direction. Recall that we are considering transverse electric modes only, and which is characterized by the electric field in the direction of propagation. That component will be 0. And in terms of Hz, we also got other components of electric field as well as magnetic field. Okay. Now we would like to further use boundary conditions and simplify this wave equation. So we recall the two famous boundary conditions, one about the electric field and one about the magnetic field. What is that? With regard to electric field, we know that the tangential component vanishes at surface of conductor. You go back to the lecture of continuity, which we have already done, and the normal component vanishes at the surface conductor. So what will the tangential component being 0 at the surface means that, so Ex should be equal to 0 at y is equal to 0 and b. It's clear from this figure that at y is equal to 0, that is this point, and y is equal to b, the tangential component here means that the Ex component should be 0. And hence, consequently, if you recall yesterday's equation, Ex was found out to be minus j omega mu by kc square del hz upon del y. So hence, when Ex is 0 at this boundary, y is equal to 0b, hence del hz upon del y should also be 0 at y is equal to 0 comma b. Now, if you see this hz is given here, right? When you differentiate it with respect to y, del hz upon del y, so the first part is constant, it is function of x. Second part is Cn sine and dn cos. So it will become, I will just write second part, it will become Cn, and then there will be this n pi by b cos of n pi y by b, plus then the other part is dn cos, so that will become dn n pi by b sine of n pi y by b. So at y is equal to 0 and at y is equal to b, right? See, at y is equal to 0, for this to be 0, so y, when we put y is equal to 0, when you put y is equal to 0, the sine part will become 0 anyways. The cos part here, for y is equal to 0, cos 0 is 1, so it will remain only Cn, so hence Cn should be 0. This is the one condition we get. Okay, and when Cn is 0, then the only term that remains is dn n pi by b sine of n pi y by b, and you check at y is equal to b, only that term will remain there, and that will also be 0 because sine of when you put y is equal to b, so it becomes n pi, which is always 0 for integer n. So with boundary conditions, we got one more simplification, that Cn is 0. Also, boundary condition will imply Ey should be 0 at boundaries, that is at x is equal to 0 and a, that is a tangent component. Okay, and hence from previous relationship, last class relationship, Ey is also equal to j omega mu divided by kc square del hz upon del x. Hence, when Ey is 0 at the boundaries, it means del hz upon del x should also be 0 at the boundaries, at x is equal to 0 comma a. So it's a simple exercise. You differentiate hz with respect to x, put that equal to 0, you will again get that this am constant should be equal to 0. So you go back to this equation, am constant is 0, Cn constant is 0, hence the wave equation gets simplified as hz is equal to some constant h0z cos of m pi by AX, and here is the simplified form where HOZ is a constant. Definitely what this constant will be, it will be product of BM and DM, right? So that is well known. So HOZ will be BM and DM, the product of these two. So constant amplitude. So this is the equation, and we can also get electric field component. So if you differentiate this del Hz with respect to y and then use this relationship, Ex is equal to this, you will get Ex also. Very simple exercise. Ex is equal to some constant E0x. Again, this constant will depend upon mu and Kc, omega, and of course Bm. Cos of m pi by Ax, and then this sine of n pi y by b e to the power minus j beta gz. So what we call this as, this is the TE-Mn field equation in rectangular waveguide. Now why TE? Because transverse electric wave, because the component in the direction of propagation z is 0, right? What is Mn? Mn are the two integers. They will now define something called mod. Similarly, you can use other relationships which we derived yesterday from Maxwell curl equations, and you get other components. I will write directly about Ey, Ez is 0, Hx, Hy, and Hz we have derived. I will write them directly here. So these are TE-Mn field equations for rectangular waveguide. We recall that we have the cutoff wave number Kc, which we last time in previous lectures defined as Kx square plus Ky square, but you know that Kx, Ky are now m pi by a square plus n pi by b square. Okay, and this Kc is also equal to omega c under root of mu epsilon. These relations we have derived. Go back and see it in the previous lectures, and from this we can get the cutoff frequency. Fc is equal to 1 over 2 pi Kc under root of mu epsilon, which is equal to 1 over, or sorry, Kc will be here in the numerator. So it will be 1 over 2 under root mu epsilon under root of m square by a square plus n square by v square. Similarly, the propagation constant or phase constant beta g is defined as omega under root of mu epsilon under root of 1 minus fc by f whole square. So whatever the cutoff frequency will be, accordingly the propagation constant will define, and phase velocity is defined as omega by beta g, which is vp upon under root of 1 minus fc by f whole square. So where the phase velocity without any medium, without any guide is, that is in free space, is 1 over under root of mu epsilon, unbounded dielectric. Unbounded means there is no metallic guide like a waveguide we have here, rectangular waveguide. So for that, now we also define something called characteristic wave impedance, as we have done it. Characteristic wave impedance, we call it characteristic wave impedance of TE-Mn mods in the guide, and we have defined it. Its notation is Zg, and it is defined as electric field component in x direction divided by the magnetic field component in y direction, also defined as minus Ey over Hx. Okay, this also we have this definition we have got from previous analysis in the previous lectures, and it was found out to be omega mu divided by beta g, and which is eta divided by under root of 1 minus fc by f whole square. You recall that eta is the intrinsic under root of mu over epsilon, that is the intrinsic of in unbounded medium. Okay, so it means that when the same electromagnetic wave was propagating without any waveguide, eta is its intrinsic impedance, but when it is confined to a waveguide which has a particular cutoff frequency, okay, below which it will not allow the EM wave to propagate, then its impedance is changed like this. It changes like this. Okay, and correspondingly we will have a wavelength also, right? Because when you have phase velocity and you have cutoff frequency, so you will have wavelength also correspondingly. So you can use the relationship, and the relationship is that wavelength is defined to be the velocity by frequency. Okay, so if you see the wavelength in waveguide, let's call that lambda g, that will be equal to the phase velocity in waveguide vg divided by the frequency. Okay, and we just now wrote here what is vg. Vg was written in this way. Okay, vg is equal to vp divided by under root of 1 minus cutoff frequency by frequency square, and there is f here. Now what is this vp by f? It is the wavelength of the EM wave without any guide, without any in the unbounded electric, without any rectangular waveguide. So we call it simple lambda. So it is lambda divided by under root of 1 minus fc by f whole square. So this is the wavelength in waveguide of the TEMN modes. TEMN modes. Okay. Now you see clearly this is the cutoff frequency, and it depends upon the dimension A and B of waveguide, as well as these which we call as mod numbers or modes, the value of m and n. So for different values of m and n, as well as for different dimensions of waveguide, there will be different cutoff frequencies for every waveguide. So in the book also there is one table. I will repeat some of the values there and give some idea about the wave, the cutoff numbers of various waveguides. Various modes of the waveguides. Now before I make that table, let's see clearly that there is one trivial case which is not it has not useful at all, that is m is equal to 0, n is equal to 0. Okay, so that is the case we will not be interested in, because that amounts to as if there is no waveguide. So because it will become the usual frequency. Now what is the next value of m and n which will give us the minimum critical frequency? That is what we are interested in. So the one of the thing is, I think it is m is equal to 1 suppose, and n is equal to 0. So when we put m is equal to 1, n is equal to 0, that is called TE10 mod. Okay, now let's write it here. So frequency for TE10 I will write as f10. It will be equal to 1 over 2 under root mu epsilon under root of m square, that is 1 over a square, and the second term is 0, n is 0. Okay, so it is 1 over 2a under root of mu epsilon. This is for TE10 mod. So we will make this as the base we can say equation, and we would be interested in the ratio of a and b. So suppose the dimensions a and b, a by b, they can be 1. So there is a specific choice for it, 1.5, also 2 and 3. Although this 2 is very famous, that is a is kept twice that of b in most of the rectangular waveguides. Okay, and then what will be the ratio of cutoff frequency for a particular value of m and n divided by fc at 10, and throughout we take definitely a greater than or equal to b. Okay, so now whatever be the ratio of a and b, TE10 depends only on a. Okay, and we can say that the ratio of frequency for this TE10 mode for A by B equal to 1, that is always 1. So this is TE10. Now whatever be the dimension ratio, whatever be A by B, suppose it is 1.5, it will be still 1. Suppose it is 2, it will be still 1. Suppose it is 3, it will be still 1. Even if it is infinity, it will be still 1. Because you see here, the TE10 cutoff frequency does not depend on B. It depends only on A. So whatever be the ratio of A and B, it will always remain same. The ratio of definitely TE10 mod with itself. Now let's consider another, that is TE01 mod. So TE01 mod means that M is equal to 0, N is equal to 1. Okay, so when we put that, we got F, I will write here 0 1 is equal to 1 over 2 under root mu epsilon under root of, so first term is 0 by A square plus 1 by B square. So it is 1 over 2B under root of mu epsilon. Nice. Now what will be the ratio? Now see, I will write here. So we had F10 as and F01 as. So the ratio of F01 divided by F10 will be, so it will be simply F01, so it will be A by B, right? A by B. And if definitely A by B is 1, then this ratio will also be 1. So it means the frequency of the TE10 mod and TE01 mod is same if the dimension of waveguide are same. Okay, now if definitely if A by B is 1.5, so whatever be the ratio of A by B, same will be the ratio of F01 and F10. So if it is 1.5 sorry, if it is 1.5, it will be 1.5. If it is 2, it will be 2. And if it is infinity, if A by B is infinity, that is A is very large than B, then definitely this ratio will also be infinity. Similarly, you can check with other mod. You can check with TE20 mod. For that you put M is equal to 2, N is equal to 0. TE30 mod, and then we have some other mods. Let's take an example of TE11 mod. Okay, so TE11, so we put M is equal to 1, N is equal to 1. So what will we get? So F11 is equal to 1 over 2 under root mu epsilon under root of 1 over 1 square plus 1 over 1 square. It is 1 over A square, 1 over B square. Okay, 1 square. So this is the F11, and we will see that for F10 we know is 1 over 2A under root of mu epsilon. Now what will be the F11 divided by F10? That will be equal to under root of 1 over A square plus 1 over B square divided by 1 over A, which will be equal to under root of just check it, 1 plus A by B whole square. Okay, now you can see that if A by B is 1, then the ratio of TE11 cutoff frequency mod and TE10 mod will be equal to root 2. Okay, similarly if A by B is 1.5, then F11 divided by F10 will be equal to root, so you compute root 3.25, which is equal to roughly 1.8. okay, 1.80 something. Okay, so similarly you can find ratio of cutoff frequency for any TEMN mod divided by cutoff frequency for TE10 mod, which we will write in short as FMN divided by F10. This will play an important role, which we will explore further later on. So we have now done this. Now there are some more terminologies One important thing is there is something called a degenerate mode. Degenerate mode. What does degenerate mode mean? When if two or more modes have same cutoff frequency. As an example, TE 10 and TE01. We saw that their cutoff frequency F01 was same as F10. So we call them degenerate mode. You will later on study this TM mode, which you will do yourself, because that has the same analysis. I will tell you that. There we will see that there are a lot of TM mode. What is TM mode? TM mode means if instead of EZ we have BZ, sorry, not BZ, we write it in terms of intensity HZ. Magnetic field intensity component along the direction of propagation is 0. This is called TM wave. Okay, so the analysis will be same, exactly same. The equations will be almost similar. There will be difference of sine and cos. That is it. The main difference will be in TM mode. You will have EZ wave equation, which you will get first. That will be of similar form. E naught Z sine of m pi x by a cosine of n pi y by b e to the power minus j beta dz. The role of hz will be replaced by ez, and there will be similar other equations. So there also we will have TM modes, TM10 mode, TM01 mode, and so on and so forth. We will see that lot of TM modes have same cutoff frequency as lot of TE modes. So they are degenerate. We will call them degenerate. Also, the mode with the lowest frequency is called a dominant mode. So in this case, you saw that TE10, hence also TE01. These two have the lowest cutoff frequency, so they will be called the dominant modes for rectangular waveguide, provided the A is greater than B. Yes, that dimension is very important. So we usually talk about TE10. TE10 is a dominant mode, because if you see for any ratio, whatever be the A by B, okay. I have copied the table here. You can see here that whatever be the ratio. So here is the ratio A by B, dimension ratio. Whatever be the ratio, if it is A by B is 1, then you can see that TE10 and TE01, they are the dominant, both are dominant modes. Their ratio of cutoff frequency is 1, and for TE11 as well as TM11, the ratio is more, then it is increasing. So in case of A by B is equal to 1, TE10 and TE01 are dominant modes. But if you see for any dimension, for any A by B, it is always TE10, which is having the ratio 1, which is the dominant mode. TE01 you see for A by B is equal to 1.5, the ratio is also 1.5. So it means that its cutoff frequency is 1.5 more than the TE10 mode. So overall, for rectangular waveguides, whenever the A is greater than or equal to B, TE10 will be is the dominant mode in the case of rectangular waveguides. That should be clear. Okay. Now look at in the book, there is a numerical immediately after this section. Kindly do it. Very simple. You are given the dimensions of a rectangular waveguide, and you have to find which operates in TE10 mode. You have to find cutoff frequency, group velocity, and wavelength. It should be very simple. Now, TM mode in rectangular waveguides, you have to do it. You have to submit lecture notes of that. It is exactly same. There is no difference in the analysis at all. Very easy. So kindly do that. With this, we are completing the TE and TM modes for rectangular waveguides, at least the analysis related to the frequency. Now we will do some further analysis, and our main goal is to study some excitation modes in rectangular waveguides, and we will study some how we put RF input into the waveguide and how we put the probe. Circular waveguides, as I told, we will not do detailed derivation. The analysis is the same, the equations are different, of course. There also you have different modes. But we will not delve into too much depth there. So we will then try to do some couplers, directional couplers, and in particular the we call something as S matrix of different microwave devices, and that's actually a topic called microwave components. So we'll be doing that very soon. Microwave components, we'll do a couple of components in detail so that you become familiar with it, and you can later on for learning purpose do other components, microwave components of your own. And then we will need a couple of lectures on definitely microwave devices. One is the microwave tubes like electron, and we will also do semiconductor devices, especially gun diode. Okay, so thank you for this lecture, and kindly note that you had to do TM modes yourself. Okay, that is same. Submit the lecture notes along with this. Okay.